next we will look into a few programming examples for this 8051 system. So, 8051 microcontroller we have seen that it can do many instructions, and it can we can use it for designing many embedded applications. So, we will see some programming examples of 8051 to get a better understanding of how this system can be made into use. So, first example that we will look into is like this, that we assume that there are 10 bytes of data that are stored from RAM location 50 hex, and then we want to compute the average of these numbers and store the result in the memory location 40 hex. And then for the code fragment we will try to see what is the size of the program and what is the time needed for its execution, assuming that the crystal that we have is 11.0582 megahertz. Okay. So, the program that we will try to write is like this. So, it will be having this 50, it will be having this this 50 hex number. So, it is the memory location from the RAM location 50 hex, the numbers are stored from RAM location 50 hex onwards, the numbers are stored. So, this is 50 hex. So, what we do first, in the R0 register we move the value 50 hex, because this R0 will be using as the index to access this 50 this memory location. So, first in the R0 register we move the value 50 hex, and there are 10 numbers, and that count we move into the register R5. So, move R5 comma hash 10. So, since this is a decimal number 10, so we do not put a h there. So, we just write hash 10. Then we say like move b comma R5, just to keep a count that it is in the b register, we will be using that value for incrementing and all. Then with this count value for averaging purpose. So, this will be necessary. So, we just store this in the b register. Then this accumulator register will be accumulating the sum. So, for that purpose we clear this a register, so that it is cleared now. Then I have to add these successive values to the a register. So, for that purpose, so I can use this instruction add a comma at the rate R0. So, whatever be the content of the first location, that will be added with a register, and a register content is previously 0. So, with that if R0 is added, so it will be the first number will get added. Then I need to the R0 should be incremented, so that it points to the next register, next number. So, increment R0, so it will point to the next register, next data. And then in R5 we have got that count 10. Okay. So, we just do a decrement jump not 0, decrement jump not 0 R5 comma say loop, where loop is this instruction where I am getting it from the memory location and adding it, add a comma at the rate R0. So, this instruction, this is the loop. So, once we are at this point, so our job is over as far as the addition is concerned. The next thing that I have to do is to compute the sum of the average of these numbers, and in the b register I already have kept this count 10. Okay. So, I have to just divide it a by b. A register has got the sum, b register has got the number of numbers. So, I say div a b. Okay. The div a b instruction. So, this will be having this a divided by b, and then the value that I get in the a register is the quotient, that is the average value, and that average value you can move to the memory location say 40 hex comma a. So, in memory location 40 hex we are moving the, sorry, this is not hash should not be there, because that in that case this will mean that this is an immediate value. So, we are trying to say that this is a memory address. So, move 40 hex comma a. So, this can be used for moving the value of A onto memory location 40 hex. Now, so this program does this. Now, if I want to compute what is the size of this program in terms of number of bytes, what is the total size of this program. So, the first instruction, so this takes 2 bytes. So, for that purpose you need to consult the manual of 8051, but essentially one thing we should understand that every instruction there will be an opcode which will be taking 1 byte, and another byte will be required for holding the immediate value. So, that is this has got this is 2 byte. So, this is also 2 byte. Then the next one, move B comma R5. So, this is 1 byte, clear A is also 1 byte, move A comma at the rate R0. So, this is also 1 byte. So, this is also 1 byte. Then this DJNZ instruction. So, this is a bit complex, because apart from this opcode I have to tell this loop address also, and loop address, since this is a 16-bit value. So, it will be a 3 byte instruction. 1 byte will be holding the opcode for DJNZ R5, and the other 2 bytes they will hold the address of this loop. So, this label loop. So, that address is 3 byte 2 byte. So, total instruction is 3 byte. Then this DAB is again 1 byte, and this instruction is 2 byte, because it has got an immediate value 40. So, that will take 1 byte, and this move A. So, that is taking 1 byte. So, if you sum them up, then this number turns out to be 14. So, total size of this program is 14 bytes. Fine. So, next that you may be interested to calculate is what is the speed, what is the time required for executing this instruction. So, for that purpose you need to find out the time needed for executing each of these instructions. So, if you consult the manual, then you can find that the machine cycles needed for various instructions. For the first instruction, so this is this will take 1 machine cycle. So, this will also take 1 machine cycle. So, this will also take 1 machine cycle. So, this DAB it takes 4 machine cycles, and apart from that, so this and this DJNZ, so this requires 2 machine cycles. Apart from that, if you look into the manual of 8051, you will find that all others they will take only 1 machine cycles. All of them take 1 machine cycle. So, if you are just trying to compute what is the total number of machine cycles needed, so it is 1 plus, so this is this one, then this one, 1 plus 1, then this one, then this one. Now, the next instructions like 1, 1 and 2, so they are repeated 10 times. So, next is 10 into 1 plus 1 plus 2. Then it takes 4 machine cycles, this one, and this takes 1 machine cycle. So, if you sum them, then this whole thing turns out to be 49 machine cycles. It is 49 machine cycles, and I have said that clock frequency is taken to be 11.0582 megahertz. So, one machine cycle is 1 upon 11.0582. So, this the 1 upon 11.0582 megahertz. So, this number multiplied by 49 such clock cycles. So, this time turns out to be, if you calculate, so this is about 4431 nanosecond. So, this way in an assembly language program, so you can compute how much memory it will take and how much time it will take. So, that is a very so that is the very strong point of assembly language programming, because here you can tell exactly how much time will be needed for executing the program and how much space the program will take. Whereas, if you are writing some program in high level language, so it is you cannot tell it correctly. So, you have to first compile the program, and it depends on the compiler like how much time it will take for doing those things. okay, for how the code will be translated and all that. That is why for getting the most predictable operation, so we should go for this assembly language programming. So, next we will look into another example program, so which is slightly more complex. So, we assume that there are 10 bytes of data stored from memory location 3000 hex in the external memory, and we want to sort them in ascending order. Okay. So, we want to do that. Now, how to do this type of programs? So, for doing this type of programs, so it is starting at memory location 3000 hex. From memory location 3000 hex, the numbers are stored, and there are 10 such numbers. So, it is said that there are 10 such numbers stored, 10 numbers. Okay. So, first of all, for writing this type of complete programs, so we will do it like this. So, we will introduce some special notations which are known as assembler directives. Okay. So, while writing any assembly language program, okay, let me just introduce those things first. Like if you look into any assembly language program, then you can find several components in it. Assembly language program, so you can find that there are several components in it. The first component, the first type of things that you can find out are the machine instructions. So, this is actually the instructions that that processor supports, like move, add, sub, jump. So, all those things. So, they are the machine instructions. So, apart from that, you will find some more and they are often called opcodes, because they are the operation code. So, that is called opcode or machine opcode. Then you can find another type of entries which are known as pseudo opcodes. So, pseudo opcodes, they mean that they are actually not for execution, but they are required for making the program structure better, and they are useful for defining particularly the variables. Like say this particular case, so you want to have this thing that from location 3000 hex, from location 3000 hex I will have 10 numbers, as I said. So, you can if you want to initialize this thing. So, while executing this program, we are assuming that okay, those location 3000 hex, the values are already there. Okay. So, you can do that by putting one particular pseudo opcode which is known as DB. DB stands for defined byte. So, if so this defined byte, so if in your program somewhere if you write like say DB 20, so what it means, what the assembler will do is that whatever be the address at this point, at that address it will put the value 20. Okay. So, what is the meaning of it is up to the user definitely, but it will put the value there. So, that way if you have to define a string, so you can define a string like say I can say like S DB hello. So, I can define a string like this. So, what the assembler will do, whatever be the address at which it finds this, it finds that it should be allocated to S. So, it will in the first character, first location it will put H, second location it will put E, third location it will put L. So, it will do like that. So, it will initialize a portion of memory with this particular string. Okay. So, these are the pseudo opcodes. So, we will be using them, and another category of words that you can find, they correspond to assembler directives. So, these assembler directives are for telling the assembler what to do, what the user is looking for, like what to do. Like one assembler directive is say org. Say if the org is followed by some address. So, if I say org 1000, that means after that if I have a move instruction, move say R1 comma R2, that means this instruction, the code for this I want to put at memory location 1000. So, when the instruction, the program will be loaded, this instruction will be loaded into the memory location 1000. So, if you know the address at which your program should be loaded, so you can put this org statement at in your program to tell that your program translated code should assume that the origin of the code is that particular address. This helps in the jump instructions and all, because jump we need to compute the actual target address. So, if the org value is there at the beginning, so you know that the program, the first statement of the program is starting from that address. Or sometimes we have seen that we have got interrupt service routines. The interrupt service routines, they are to be loaded from a particular address. So, before writing that interrupt service routine, so you can put an org statement here. So, that way, and whatever be my target address, so that value can be stated here. So, that this interrupt service routine, when it is translated, so it is put into the exact interrupt vector, the ISR address, whatever is required for that. So, that way we have got assembler directives, and there are many such assembler directives. One of them is say org, another one that you have is EQU, equality. So, this is something like some constant definitions. So, some constant definition. So, you can define something like in high level programs, we are like programs like C, C++, we are writing like hash define x 5. So, the 5 x is a constant whose value is 5. So, here also you can have this EQU type of definition. So, like say I can have say n EQU 10. So, n is a constant whose value is 10. So, unlike this DB, this n is not assigned any memory location. So, in the assembled code you will never find this n having the as a location, but wherever in the program this n will occur. So, it will be replaced by 10 in that program. So, with this we will be trying to write this code for this program, where from location 3000 hex, from location 3000 hex I have got 10 numbers stored, and I want to sort those 10 numbers. So, I assume that since the program is there is no other program in the system, my program originates at address 0000 hex. So, if you know that if you know some different address in your system, your RAM may be from some different address. So, then you can put some other value there. Then this n I take it as a constant, which is 10. So, that later on if tomorrow I have to sort 20 numbers, so I can just change this value from 10 to 20. Okay. So, I do not need to change the entire program. I take another temporary location, which I call temp, for doing this exchange basically, and I take the location 50 hex for that purpose. Okay. So, this 50 hex is a temporary RAM location, which I will be using as a scratch pad for exchanging the variables if exchanging the data items if they are out of order. Then, so the start address is told to be 3000. So, I take another constant start, which is start EQ 3000 hex. So, this is the when I can write in terms of start. So, tomorrow if I have to sort an array starting at address 4000, so I just need to change this point in the program, and rest of the program will remain unaltered. Then I take a counter like move R4 hash n minus 1. So, n is 10. So, I take this, so this will evaluate to 9. So, you see that this statement is actually the statement like move R4 comma 9. But if I write 9 here, so tomorrow if I am asked to sort for 20 numbers, I have to change this point also in the program. But if otherwise I can just change this number 10 to 20, and this part will be working as it is. So, there is no problem with that. So, we will be following that philosophy. Move R4 comma hash n minus 1, then the DPTR should be set to that start address. The DPTR is having the start address, the 3000 hex is coming to the DPTR. Then we move this R4 value to A for and this and then move this A value to R5. So, this is done to just move R5 move this R5 A to R5, so that we can do some more comparisons, and then I get the first number in the A register. So, move x A comma at the rate DPTR. So, from the DPTR so from the location 3000, so the value is coming to the A register. Actually these two statements, so they are actually moving this R4 value to R5. So, I cannot directly move R4 to R5. So, I have done it like this. So, you can of course replace these two pair by putting a statement like move 5 comma 4. So, that can be done, but it is not done here, they are put as two separate statements. Okay. So, you can have this move x A comma at the rate DPTR. Then we do like move R1 comma A. So, the value of A is moved to R1, then INC DPTR. So, that now it is pointing to the next entry 3001, and then move x A comma at the rate DPTR. So, the next number it will be coming to the A register, and then we save that value into a temporary location. In a temporary location 50 hex we save that value, and then in R1 we had saved that the first value that we had read in R1. Then we have got the next value into the moved on to the temporary register. Now, from R1 I take it back to the A register, so that I can do a comparison. So, move A comma R1. So, now the situation is the value that we had at 3000 is in A register, and value that is there at 3001 is in the memory location temporary. So, I can do a comparison. CJNE type of instruction can be used. CJNE compare jump on not equal A comma temp comma L3. Okay. So, L3 will come, it will be jumping to otherwise I have to jump otherwise the numbers are they are not same. So, if they are not same, they are it is jumping to L3, then it will otherwise it is make a jump to L4, and this L3 it will be checking whether some carry is generated. So, if the numbers are same, if the numbers are same, then I do not need to interchange. So, it will be it will come to this SJMP L4. So, it will be jumping over to this, otherwise I do not need to change this thing. So, then after that I move x at the rate DPTR comma A. So, it is so this A register, so content was bigger. So, that is now moved to the L4 to the memory location 3000. So, A is greater than temporary. So, now I need to exchange. So, this is the first step of that exchange. Then move A comma temp and then we have to go back in the DPTR. So, we do a decrement of this DPL register. So, we cannot decrement this DPTR register. So, because that is 16 bit. So, we have to do DEC DPL and then move x at the rate DPTR comma A. So, this temp value has been moved to A register. So, this temp value has been moved to A register. So, this move x instruction, So, this will take that temp value to the previous value to the previous location, that is the 3000. So, between 3000 and 3001, so it will do an exchange. Then again we do an INC DPL, and then in L. So, that is the completion of one comparison and exchange. So, then I have to see whether I am done with the comparison. So, this is done by this check DJNZ R5 comma L2, where L2 is that instruction, this instruction is L2. So, I need to take the decrement R5, and if it is not 0, decrement jump on not 0 R5. So, it will come to this L2, so that I can take the next number from the memory. So, DJNZ R5 L2, and so this will be completing one loop. So, on top of that we should have another loop. So, that is by R4. So, DJNZ R4 R4 to L1, DJNZ R4 L1, where this L1 is where L1 is the location of this one. So, L1 is this one. So, this is starting the next iteration of the outside loop. So, for comparison, you know that for the sorting, you know that we should have two loops, and those two loops they will be operating in a nested fashion. So, we create two loops here, one in L1, another in L2. So, that way it goes. So, this way we can have this program developed. Okay. So, if you just trace through the program, so you will see that this is actually doing the sorting. So, after this, so this will be repeating till R5 becomes 0, this will be repeating till R4 becomes 0. So, after this we have this one, and then we have got another statement to end a program. So, which is called end. So, this is also another assembler directive. So, this is telling that the translation process will be ending at this point. So, I should not do no more translation will be required. So, this is useful because many times what happens is that in the development phase of the program, so we write many routines and we do not want to really put them into our final code. But if there is something happening in the final code, then maybe for debugging purpose we need to revoke those codes again. So, for that job, so this end directive can be useful, like when I am so if this is the complete program that I have written, and maybe finally I see that I need only this much of program for the correct operation of the system. So, at this point I put an end in my assembly language file, so that this part is not translated. So, this part is not translated into machine code, but I do not delete this part, because later on what can happen is that there is some bug that is that has come up, or some augmentation has to be done, then this routine will become part of this routine. Okay. So, in that case I can just shift this end point to here, and just shift this end point to here, so that I do not have to just I do not have to readjust everything. Okay. So, I do not have to rewrite the program together. So, this way we can have this program translated into machine code, and the selective portion can be taken. Now, when you are doing this translation, like the program that we are writing, so they are the assembly language program, maybe the name of the program is say program 1. So, this normally has an extension of ASM prog1.asm. So, when this is passed through the assembly process or the assembler, so it produces a number of output. One output is definitely the executable version. So, this program translated code, the machine code. Another output it produces, so which is known as the list file. So, this program code output, so this is for the processor to understand, but this list file, so this is for human understanding. And in this list file, so we have got this program statements and their corresponding codes. So, if I have got a statement like move say R1 comma A, then what will happen is that in the list file. So, first the corresponding address will be there at which this statement is being put, the address will be there, then the code, the corresponding code that is generated for doing this thing operation. So, for this instruction, that code will be there, and then the instruction will also be written here. So, this way for the entire program, all the statements they will be shown, they will be written one after the other, their addresses will be shown and their addresses will be shown and also the code will be shown. So, this helps in understanding whether the program has been translated, the program has been written correctly, or we can understand whether the program has been translated correctly, whatever we were looking for, whether that has been done or not. And also if there is some error in the assembly process, then they can be flashed. So, this error messages may be somewhere here. So, we understand that while translating this statement there was some error. So, we can rectify this error in this ASM file and again give it for assembly. So, this particular file is called the list file. So, I would suggest that whenever you are doing assembly language programs, so you take help of some assembler, okay, because the languages are complex. So, you take help of assembler and do look into the list file that is produced. Okay. So, apart from this code, so code will not understand anything because that is a binary file, but this list file is a text file. So, you can have a look into this text file and see what is there in the translated version of the code, and if there is some error, then of course, we can see the error and then go back and correct the assembly language file.